The Williamson Ether Synthesis is a classic organic reaction used to create asymmetrical ethers. By reacting a nucleophilic alkoxide ion with a primary alkyl halide, we can build complex molecules essential for pharmaceuticals and industrial solvents. Our goal is to form a new carbon-oxygen bond. This process typically follows an SN2 mechanism, where the alkoxide attacks the electrophilic carbon, displacing the leaving group in a single, concerted step. In the SN2 pathway, spatial orientation is everything. The nucleophile must approach the carbon from the side opposite the leaving group. This requires an unhindered path, making the structure of our reactants critical for success. However, alkoxides are not just nucleophiles, they are also strong bases. Instead of attacking the carbon, they might grab a neighboring hydrogen atom, triggering an E2 elimination reaction that produces an alkene instead of an ether. This competition determines our final yield. Whether we get the ether we want or the alkene we don't depends on three main factors: the substrate structure, the bulkiness of the base, and the reaction temperature. The degree of substitution on the alkyl halide is the most important factor. Primary halides are wide open for SN2 attack. As we move to secondary and tertiary halides, the path to the carbon becomes blocked, favoring elimination. With tertiary alkyl halides, steric hindrance is so high that the SN2 reaction cannot occur at all. In these cases, the alkoxide has no choice but to act as a base, leading exclusively to E2 elimination products. The size of the alkoxide also matters. A bulky base like potassium tert-butoxide is too large to navigate into a crowded carbon center. Even with primary halides, bulky bases will often favor elimination over substitution. Let's look at synthesizing methyl tert-butyl ether, or MTBE. We have two possible sets of reactants. One path uses a bulky alkoxide and a simple halide, while the other uses a simple alkoxide and a bulky halide. In path A, we use methyl iodide. Because there are no beta hydrogens and zero steric hindrance, elimination is impossible. This is the perfect setup for a high-yield Williamson ether synthesis. In path B, we react methoxide with a tertiary bromide. The methoxide cannot reach the central carbon. Instead, it removes a proton from one of the methyl groups, resulting in an alkene. This path fails to produce the ether. With secondary alkyl halides, the competition is fierce. Using a strong base like ethoxide usually results in elimination being the major pathway. To favor the ether here, one would need to lower the temperature significantly. Temperature acts as a fine-tuning knob. Elimination reactions increase the number of molecules in the system, which increases entropy. Therefore, higher temperatures favor the E2 pathway over the SN2 pathway. To successfully plan a synthesis, always assign the less sterically hindered alkyl group to the alkyl halide. If you have a choice between a primary and a secondary group, the primary group must be the halide to ensure substitution. To summarize, Williamson ether synthesis works best with methyl or primary alkyl halides. Secondary halides give mixed results, and tertiary halides yield only alkenes through elimination. Apply what you've learned. If you need to synthesize ethyl isopropyl ether, would you react ethoxide with isopropyl bromide, or isopropoxide with ethyl bromide? Think about the steric hindrance on the halide. The correct choice is isopropoxide and ethyl bromide. Since ethyl bromide is a primary halide, it minimizes steric hindrance and prevents the E2 pathway from taking over. This ensures a clean synthesis of your desired ether. Generated by Vision Solve AI.